Hello everyone, let's continue with multiple regression. So what I want to cover today is to take a quick review of multiple regression that we've looked at so far, and then also get into the situations where we are talking about PA minus PC being greater than 1, but also where PC is greater than 1. So we'll take a look at that in a few moments, but first, let's just take a look at multiple regression and what we've done so far in these screencasts. So, to remind you, some of the variables we're using are year-end score as the dependent variable, age, parental income, entrance exam as the independent variables. So let's go ahead and take a look at this model comparison. And essentially what we would do here is just simply add these three variables in SPSS. And in the ANOVA table, we will have model C as the mean only model, as is the default. So let's go ahead and take a look at that. So what we can see here is we have final grade after year 1 as the DV, age as X1, parental income as X2, entrance exam as X3. So we could go here and ask for 0 part and partial, we could ask for collinearity, but I want to just directly request the part and partial as well as the tolerance values. So to request the part and partial, we can just enter the letters ZPP on the statistics line. And this stands for 0 part and partial that you've seen hopefully in the coefficients table, either in the assignments, problem sets, or in the previous screencast. To request the tolerance values, I can just type TOL. So along that statistics line, I've entered these two sets of letters. I will get the 0 part and partial correlations, and I'll get the tolerance. So let's go ahead and do that. There we have it. So right away, we can see that this model, using all three predictors, explains about 24.7% of the variance in final grade after year 1. The F value of 6.115 has a p-value less than 0.05, so that's a significant proportion of variance. Therefore, this full model is a significant model, statistically significant, in explaining final score. We should note that the R-square is 0.247, so approximately 75% of this variance is unexplained. So we can make an argument this is a weak to moderate model. Now remember, we're trying to explain something that's quite challenging, so we don't expect to see this score up in the 0.8, 0.9. We're trying to explain academic performance, which can be very difficult to do. All right, so we know the full model is significant, and that answers our model comparison here that's listed right here. However, there are a lot of other model comparisons and or hypotheses that we're testing within SPSS when we run this because of the coefficients table. The coefficients table tells us about each predictor controlling for all others. So note that PA minus PC is equal to 1. So the child's age here is not a significant predictor of final grade after controlling for parental income and entrance exam score because the t-value of negative 1.816 has a p-value greater than 0.05. Likewise, parental income is not a significant predictor of final grade because the t-value of 1.691 has a p-value of greater than 0.05. However, school entrance exam score is a significant predictor, controlling for age and parental income because the t-value of 4.012 has a p-value of less than 0.05. One thing I should note here just about the output is that we have a t here. I believe in assignment 2 you were asked for an F score, or previously in an assignment or problem set. You can simply go back to the syntax and add F here, and it'll convert that t into an F. It's not really necessary because we know that when PA minus PC equals 1, t squared is equal to F. So if I want the F statistic for these predictors, I can just simply square these. Now, why am I ignoring the constant? Because I don't particularly care about the constant in this case, and in the vast majority of cases, almost all, because the constant would tell us what happens at the point equals 0 for all other predictors. Well, I don't particularly care at age 0 what this constant tells me. Likewise for parental income or the entrance exam score. All right, moving over to partial and zero order, as well as the tolerance. So correlations, the zero order should be noted that is simply the only part of this coefficients table that does not relate to all of these predictors being in the model. So said another way, this 0.109 is simply the correlation between child's age and final grade. It doesn't control for anything else. So if we were to ask SPSS for the correlations, these are the values we'd get. The partial correlation we've covered in the previous screencast, but if I want, for instance, the proportion of variance that school entrance exam predicts in final grade after year 1, controlling for age and parental income, it's a mouthful of course, I can square this value and I'll have that number. This is just the correlation, so if I want the proportion of variance explained, then I need to square this number. All right, tolerance here, it should be noted that tolerance, the calculation of tolerance, go back in the notes and see, has nothing to do with final grade. All tolerance tells you is how independent this variable of age is with respect to the two other predictors in the model. That's all it is. And we know that a value of 0.1 or 0 should raise alarm bells. Now it's continuous, so that's just a cutoff. It's just a point of reference to consider. But since we're using it, all of these values are far above 0.1. We don't have to worry about the overlap among the predictors. Okay? But the one thing important here, and one misconception sometimes, is that tolerance in some way is related to final grade. It is not. It is only related to all the other predictors in the model. Okay, then VIF is simply 1 over tolerance, so it's a redundant measure of redundancy, as it's often called. Okay, so let's go now to the next point I wanted to discuss. So the next point I want to discuss is when we have PA minus P greater than 1 and PC greater than 1. So let's take a look at this model comparison where we have x1 and x2 in model C. And in model A, we have x1, 2, 3, and 4. So this is a legitimate model comparison. Model A has everything that model C has in it. We want to know if model A is significantly better than model C. So what does that mean in practical terms? We want to know if entrance exam score and interview score together significantly improve this model when age and parental income is controlled for. All right, so this could be looked at as, do our measures of the individual student's performance do us any good beyond things that could be considered demographic or out of the student's control? We know that there's lots of relationships, and this is a complex example and topic, and again, this is fictional data, so we're not in any way trying to propose evidence to this actual theory and whatnot. We're using it as an example. All right, so let's get back to this from a regression standpoint. We want to compare these two models. Well, we could run model A and use x1, x2, x3, and x4. That'll give us the test of each of those predictors controlling for the others in the coefficients table. It will also tell us whether or not this full model is significant in predicting the final grade. It won't tell us about the model comparison we have in front of us. To do this model comparison, we need to, as always, calculate the sum of squared error for model C and model A. However, we cannot just run one of these and get both of those numbers, because if I run model C, I'll have the error for model C and I'll have the error for the mean-only model. I won't have any error for model A. Likewise, if I run model A, I'll have the error for model A and the mean-only model, but not the error for model C. So how do we go about doing this? Well, one way, to this point that we've discussed, is to simply run the two models and find the error for each, and then calculate PRE and F. So let's go ahead and do that. Because remember, PRE is SSEC minus the SSEA divided by SSEC. If we could find the error for each of these models, we could do that. All right, so let's go ahead and do it. I'll get rid of this. So in my first model, I want to get rid of this. So essentially what I want here is I want final grade after year 1 as the DV, age and parental income as the IVs. I'm just going to go ahead and click OK and get our output. All right, we could go through this output, and we can already see this is not a very strong model. But what we're really interested in is the error for model C. Well, what is the error for model C? It is 5221.523. That is the error, or the residual, SPSS calls it, for model C in our model comparison. So, SSCC is that number, 5221.523, right there. All right, I have to get the error for model A. Well, I should realize right away it's not here. Okay, so I need to go back. And find the error for model A. So now I will add in the interview score and then the entrance exam score. I just want to do it in that order because I've labeled them X3 and X4 accordingly. Run the model. We can take a look at this model. We can see that it's a significant one. It explains about 26% of the variance, etc. But what we're interested in for our model comparison is this error. Again, the residual or the error for model A is listed here, 3968. So I go ahead and add that as SSE A. I do the calculations, and the PRE is 0.2399. In other words, these two predictors explain about 24% of the variance, or 23.99% of the variance, in final score when we control for age and parental income. Is that a significant amount? We don't know. We have to convert. We could go ahead right away and look at a PRE table for this with 2 and 55 degrees of freedom, but let's transfer it or calculate it, the F accordingly, and look up the F crit. So here, this is the general formula for F. We have to realize that PA minus PC is 5 minus 3. 1, 2, 3, 4, 5, and 3. So putting in the numbers, doing the calculations, we come out with 8.681, I believe. If I go up and look at a critical table or use the web to calculate my F crit, it is with 2 and 55 degrees of freedom. That's your 2 and 55. Excuse me, this is not 55. This is that. 60 minus 5. And we have the F crit of 3.165. Therefore, this is larger than the crit value. The observed is larger than the crit. Therefore, we can say that model A is significantly better than model C, and we can say that entrance exam score and interview score together, controlling for age and parental income, significantly predict year-end score. Okay, so this is an example of PA minus PC equals to 2, and PC here is greater than 1. Which is really what differentiates it. When it's equal to 1, we use the coefficients table, but that's not what we're interested in here. We're interested in adding 2 additional predictors. You could add 3, that's fine, and you would follow the same procedure. All right, now I want to just talk about another way to do this in SPSS. So another way, and this was mentioned, I believe, in an assignment or problem set, is to do this. So again, in the first model, what we had entered was the child's age and then also parental income. We can have SPSS essentially reduce the output, combine it for the two different models we're going to run here, Model A and Model C. Going back, Model A and Model C are these two. We can ask SPSS essentially to organize this a little bit better for us, but then we can also ask for some statistics that we may not have seen already. So I click Next. When I click Next, what I'm going to add here are the other predictors I want to enter. So what do I want to enter in addition to what's already there? The interview and the entrance exam score. Let's go over to statistics. R-squared change is going to give us the change in the R-squared between the two models we've entered. This isn't relevant if we don't use the next step. But since we are doing the next step and we're asking SPSS to conduct two different models for us, or analyses of two different models, we are able to calculate this R-squared change. Again, we could ask for these and whatnot. I'll just leave that blank. Let's paste it and see what it looks like. So all that we've added really is another line for enter. So if you go back and look at other syntax for regression, you have method enter and you have the IVs. Well, what we've done here is added another line, and we've added these two, interview score and entrance exam. By doing that, we are saying keep these first two in the model and then add more into the model. Okay, so the second model is going to have all four that have been entered. The change here that you note, that's the syntax to ask for that R-squared change. We can ask for the TOL if we want. We can ask for the ZPP if we want. Let's run the regression and see what happens. Okay, one thing to note is essentially SPSS has, let's skip the model summary for now, has essentially just organized the output so that you have model 1 and model 2. So model 1 simply has the age and parental income. Model 2 has all four predictors, and you can see that here. They tell you what the predictors are. What you can notice is that these two ANOVA tables are the same as when we ran it previously. So we have the F of 0.888, the F of 4.904. You can see them here. So it's just combined the two different regressions. The model summary, however, has been expanded for the change statistics. Over here again, this is the exact same as before, but change statistics has been added. There's a bit of misalignment here in some ways that we have to be careful of. R-squared change is simply the change in R-squareds between the two models, just taking one and subtracting the other. So model 1, 0.030, is the same here because it's being compared to a model with nothing, essentially. However, this 0.233 is simply model 2 minus model 1. So this is the R-squared change. Remember, that's not the PRE for this model comparison. This is simply the change in R-squareds. Okay, if you start at 0, you get 0.030. That's not particularly interesting. What's interesting is the second one of 0.233. That is simply R-squared for model 2 minus R-squared for model 1. It's important to note that because we calculated the PRE. This 0.233 is not the proportion of variance explained by these two additional predictors controlling for the 2 in model 1. That is not what it is. We calculated it. We know that it's 0.2399. Okay, it's 0.2399, which is different. However, the F change, this F statistics of 8.681, is a test of whether or not this difference is significant. And it's really a test of whether or not this PRE is significant. It's an important distinction. Okay, so you can see that 8.681 is exactly as we calculated. The R-squared, or the PRE change, is not the same number. It's very close here because we're starting with such a small value of 0.030, but just note that. This is not the PRE for the model comparison, it's simply the subtraction in R's, or R-squareds rather, sorry. The F change is a test of whether or not this difference is significant, and it is a test of whether or not the 0.2399 is a significant amount of reduction in error. Here we have the p-value calculated for us, and that does tell us if model 2 is significantly better than model 1. So it tests this value. And you can see we have 2 and 55 degrees of freedom, just as we did in our model comparison. Our 2 and 55. Right, so this is just a way that SPSS will do that F test for you. Be wary that the F itself is the number that we're interested in. Be wary that R-squared change is simply the change in R-squared, not the proportional reduction in error for the inclusion of the two additional predictors. Right. That summarizes the situation in which we have PA minus PC greater than 1 and PC greater than 1. And there's another way to use SPSS to get at the answer directly. And here's how we could do it more manually and conducting two different regression analyses. I'll end there and